not.
Yeah.
Okay. So I made of your scores.
Should I also record?
No, I started recording.
Okay.
And shall I? Do you want me to switch on the video or how do you?
Yeah, I think it's better.
Okay, let me do that. Okay, great. So yeah, so yesterday we were looking at these the OWL syntax, right? So we start off with description logics, and then we went ahead with OWL2, which stands for the web ontology language. So it's a language used to create ontologies, and ontologies are nothing but a way to describe the facts in a particular domain, right? So we'll come to that a little later, right after this one. But there is a connection between OWL2 syntax and OWL2 itself and description logic. So OWL2 is based on description logics, and the formal underpinning behind OWL2 is description logic. So there's lots of similarities, and if you are familiar with description logic syntax, then this becomes easy to just follow, right? Okay, so we were discussing these two types of properties or roles, right? So these are properties is a term that is used in OWL2, but in description logics we use roles. So properties are nothing but roles. So there are two types of properties, right? There is this object property and data property, and so the difference between them is that object property connects one individual with the other individual. Say for example, housewife. John has wife Mary. So housewife property is connecting two individuals here. On the other hand, data property connects an individual with a data value. So something like the has age, right? John has age 51, and we also specified the data type of that value, which is integer. So that is the difference between object properties and data properties, right? So then we also looked at the domain and range. So generally, it's a good idea to associate the domain and range. Whenever you create a property, it's a good idea to associate domain and range with it. And these role characteristics, like we should check whether they are transitive, reflexive, functional, and so on. So we'll be doing that when we create this ontology next. Okay. So domain and range, it's again very similar to the concept that we have in functions as well, right? So and this acts, so this is a place where, or this one mechanism where you can sort of connect a class to a property. So you can say that the domain of has the owner is a vehicle, and the range of has owner is a person. So for example, you can say John has something like any particular car number, right? Say car number 1101 has owner John. So and okay, so for data property, the range is always a data value. So it can be either a integer, string, floating point number, and so on. Date, all these are valid ranges. And domain can be one of the concepts in the ontology. So here in this case, it's a person. So now the advantage of setting these domain and range. So we discussed one particular example yesterday, right? So let's say you have this the domain and range set for work set. So the domain of work set is employee, the range of work set is organization. And you also asserted that John works at IBM, right? Now, if you have these three statements, the reasoner can make some inferences. So it can say that based on 1 and 3, it can state that John is a employee.
IBM should be small letters, start with small I.
Yeah, right. Okay. Okay, we can, that's it. So we can do it. Yeah, that follows the naming convention. Okay, and from 3 and 4, these three lines, we can infer that organization, IBM is an organization, right? So that's the advantage of setting these domain and right? So you don't explicitly need to state that John is an employee and IBM is an organization. It's very helpful for during reasoning process. Right? So the other thing that we should be careful is having these multiple ranges. So what if you want to set multiple domains and ranges? So maybe let's say you have this range, and maybe you also want to set something like employer, right? So just giving some random example. So if you want to do this, then you need to be careful whether what should be the relation between organization and employer. So if you just do this, then it will be treated as a intersection. So even so, that's why you should be careful, right? So right now it will be treated as work set. The range of work set is organization intersection employer. So if you want it to be union, then you need to explicitly state that. So we can check that while modeling. So the same holds for domain as well. So if you do it separately, then it will be treated as an intersection. Okay. Okay, we already looked at these two assumptions yesterday, and since how2 is based on uh, description logics, the same assumptions carry over. So it also follows the open world assumption and the no unique name assumption. Right? So I'll not be going over them again. Okay. So rest of the constructs that we have looked at yesterday in the description logics, they also apply to OWL, because like I said, it follows from description logics. So for example, so the only difference is that in OWL, you have these keywords, right? Equivalent classes. So instead of the symbols that we use in description logics, it is convenient to obviously use these keywords, which can be passed by any API or library, so that it can go over all these axioms. So this simply implies that mother is equivalent to woman intersection parent. So mother is exactly equivalent to someone who is both a woman and a parent. Right? And the same thing. So we have, even for union, we have object union of, and these are the other keywords. So we have equivalent classes, disjoint classes. So mother and father are disjoint with each other. That's what this means. Complement is for negation. And we have, and you can also compose all these things together. So for example, okay, so I don't know. So let's go over this one, right? So a childless person is equivalent to person intersected with the complement of parent. So that means not a parent, right? So childless person is someone who is a person and not a parent. So that's what this means. And you can now start composing these different constructs together. So here we used object intersection of with complement along with the class assertion. Okay, so that can be done. Okay. So we also have the two quantifiers from description logics, which is existentials and universal. And it works the same way here as well. I'm going to, so I'll be going over these things pretty quickly so that we can start with the modeling part, right? Because we don't generally have to remember these keywords anyway, because we have a tool and that can translate whatever we put in the tool into this particular syntax. So we don't have to worry about the exact syntax, but generally it's a good idea to at least know what they mean. Right? So this is the same example that we talked about earlier, which is exam having an examiner who is a professor and so on. So, so if you want to say that any exam must have at least one examiner, we go about it this way. So this is the keyword for existential, object some values from. Right? So exam should have at least one examiner. That's what this is. And this is again an example of the parent. So parent is someone who has at least one child. Right? So we use things like at least one sum for this quantifier. And for universal, it's for all. So all examiners of an exam. So we use this particular keyword, object all values from. And so an exam must have examiners who should be a professor, right? So that's what. Okay. These are again some more examples of the universal quantifier itself. And again,
Yeah.
oh, sorry.
Raghava, can you go back?
This one, yeah, this is
So here, so has examiner will have exam and some individual. Yeah, that will be the pairs has examiner.
right.
And our assumption is that it may not be necessary that it may be a professor. That the person may not be a professor. Like for instance, some TA could be examined.
So are you referring to this corner case?
Yeah, I mean, I don't understand really, because how can you have a pair when you say has examiner and when you say an exam like CS101, then you cannot have, you have to have another parameter to the right side of that, no? There should be some CS101 and some John.
True.
It cannot be the case that only, it cannot be the case that there is just CS101 and there is nobody, there cannot have a pair with only one argument. Yeah.
No. Here it says 0 argument. So there is no argument even on the left hand side or the right hand side.
Is it like
Because this exam, there exists some exams that do not have any examiner at all.
Yeah, so is it like this for a particular exam there can be many has examiner property, right?
Yeah,
That
that I
can
can
be
understand.
examined.
For one exam, there
is
can be
this-
many examiners.
Yeah, so is this actually telling you that for each exam, whatever has
Yeah.
examiner relation you have defined for that exam, it should be a professor. It should not
Right.
be any
Yeah.
PA.
That is the all, yeah, for all case. So I
So
think
in
maybe
the corner
Amal
case-
was referring to this one
Yeah,
where
so the corner case,
Yeah.
the corner case means that if suppose task examiner is not defined for that particular exam, also that exam will be included here. Like task examiner relation is not defined for that exam.
Right. Yeah,
Then
that's
also
what
this
this
exam
means.
will
That
corner case means, right?
right. So even though has examiner is not defined for, yeah, you're right. So that even that will be included here. As to why
Okay.
that should be included is
Yeah, that I can understand. That is just how you will treat their existence for all. For all is vacuously true. If okay, so I understand that this for all R dot S, you will take all A in all A such that for all if whenever there is AB in R, B should be in S. Yeah.
right.
So that will be the meaning of that. Okay.
Yes.
Okay.
That is
Okay.
right.
So so here you are taking this open world assumption. So whenever you may have exams which may not have examiners, and therefore when you evaluate this query, you will also take those exams which doesn't have which are not mapped by
Any exam.
but yeah, but still I don't understand like how can you, yeah, because the evaluation of for all R dot S should depend only on R and S, no?
R and S, but R will have one argument, so it has to be related to the other exam part also. So it will have two arguments.
It will have two
yes,
arguments.
For all and there comes with a subclass, always comes with a subclass thing, always associated with a, is it so?
No, need not be, no. It's just need not be. It's just a set. Object all values from as examiner processor is a set. It's just a set.
Yeah.
And you're saying that this exam is a subset of that. So actually you can nest these things, no? Object all value stuff. Yeah.
Right. Yeah, that's the. Yeah, we can nest it. Yeah, it can go put more things inside. Yeah.
Okay. So okay. So I mean, I can understand that this is how it is done, because HAS examiner is actually taking the payer's exam and not professors necessarily, like people or employees or people or something like that. And
okay.
And
at
then,
least in this case, we want them to be professors.
Yeah, and in this case, it will be all professors. Yeah. Okay, I can understand. I can go with it. All right, let's continue.
Okay. So this is another example of the same thing, which is about happy person and having a child. So if all the children are happy, then the person is also happy. And the equivalent case, corner case for this is that even a childless person can be happy. So that's what this means. Okay. So we can go ahead with the cardinality. So there are three types of cardinality that we discussed in description logics. Right? So one is the min cardinality, the other one is max cardinality. So so this corresponds to the at least, at most, and the equal. So there's the equal cardinality, which is you state that this exact part, right? So in car has exactly one engine. So, okay, let's start with the max one, where you have this at most one. So John, if you want to say John has at most 4 children, we can use this particular keyword. And in description logics, it was the symbols, right? So we had the greater than, equal to, less than, or equal to, and equal to symbols. So for min cardinality, we have this particular keyword, but again, this is equivalent to less than or equal to in description logics. And then the exact cardinality, which is where we use the symbol equal to in description logics, right? So this is what it means. So we looked at nominals in description logics, right? Where we can specify that a class using nominals, we can create these closed classes or closed concepts, where we can say that this concept has exactly these individuals as instances. So something like the weekday, weekend exactly has Saturday and Sunday, only 2 instances, right? And the same is the case with the months in a year. So it has only 12 months. So if the number of instances are limited and they are also fixed, we can create these closed classes by enumerating all the individuals. So in this case, we are doing it for my birthday guests, and we want to say that Bill, John, and Mary are the only guests that should come for the birthday. So these are what are called as closed classes. And generally, it's a good idea to also state that Bill, John, and Mary are disjoint with each other. So that means we are following the no unique name assumption, right? So they are different from each other and they are not same. So now let's say a question can be that, okay, what happens if there is a 4th guest or a 5th guest, right? So then by default, then the assumption or the implication is that if there's a 4th guest, the 4th guest has to be equivalent to one of these 3. Or in some sense, so they are like an alias, right? So let's say apart from you state that Bill, John, and Mary are the only guests, then let's say if Jim shows up, then Jim should be an alias of one of these 3. Yeah, okay, I also mentioned that. Jeff shows up, then Jeff should be equal to one of these 3. Okay, similar to the inverse roles that we had in description logic, we can also do the same thing here. And this is the keyword that we have to use for the inverse roles, right? Like, so has parent and has child are inverse of each other. Right? So if A has parent B, then it means that B has child A. And we have all these role characteristics or property characteristics, starting with there's symmetricity, asymmetricity, and then transitivity, functional properties, and so on. So we'll quickly take a look at all these different characteristics. Okay, so has spouse is a symmetric relation. So if A has spouse B, then it also means that B has spouse A. And these are very useful again for answering these questions. So let's say if John has spouse Mary, that's what you put in your ontology, right? But if someone asks the question, who is the spouse of Mary, then unless you state that they are symmetric, this question cannot be answered, right? So it's very useful for making these inferences and answering questions. Okay, asymmetricity is again, so has child is an example where if so you can state that A has child B, but it's not the case that B has child A, right? So we can state that this is asymmetric. So has relative is an example of reflexive property. You can say that A is related to A itself, right, or himself or herself. Yeah, so irreflexive is okay. So again, it cannot be related to itself. So nobody can be one's own parent. So parent of is an example of this irreflexive object property. Okay. So has functional is an interesting one. So let's say, so if you state that has husband is a functional property, then that means, okay, in this case, Mary has husband James and Mary has husband Jim, right? But if you state that has husband is function, then James is same as Jim. So they are, let's say, alias names of one another. That's what it indicates. So you are stating that Mary should have exactly one husband, right? So there's also the inverse functional, which I don't know. Yeah, okay, we also have the inverse functional here, which means the other way around, right? So for example, if you say that has husband is inverse functional, so you can use this to state this fact that an individual can be the husband of at most one other individual, right? Okay, so those are the okay, there's also the transitive property. So again, so has ancestor, if you state it as a transitive property, then you can make these inferences. So let's say A has ancestor B and B has ancestor C, then you can automatically infer that A has ancestor C as well. These are also useful in the whole part relations, like like finger is part of the hand is part of the body, then finger is part of the body, right? So, and sub-region, it's also useful. These also a whole part relation, sub-region of. Okay, so disjoint properties. So similar to disjoint classes, you can also put this disjointness in properties as well. So we can state that has parent and has spouse are disjoint with each other, right? So that means if A has parent B, then it cannot be the case that A has spouse B. Okay. So this is the composition, role composition, or role change in description logic. So if you can, this is the uncle example. So A has father B and B has brother C, then A has uncle C. So we use this particular keyword property chain to have as many arguments as we want to. So it need not be restricted to 2 arguments, right? We can have more than 2 as well.
So it will be all binary relations and you will take the composition.
Right, yes. So for example, it's also useful for the grandparent relation. Parent's parent is a grandparent. So you use this property chains. Okay. So now, so yesterday, I think right towards the end, we discussed about the complexity, right? The trade-off between expressivity and complexity. So the more expressive the description logic is, so expressivity comes from the type of constructs that we are using. So for example, if you are using only unions and existentials, or maybe subclass existentials and intersections, then it may not be as expressive as, let's say, if we include cardinalities as well. So cardinalities will increase the expressivity, but with more expressivity, the trade-off is that the complexity, the reasoning complexity also increases. So that's why there was a need to come up with these fragments, right? A smaller pieces of the description logics that are more efficient in terms of the reasoning time. So people have come up with these polynomial time reasoning fragments. So OWL2 itself it has very high complexity. So but if you have a smaller fragment, so these are all the smaller fragments: OWL2, DL, EL, QL, and RL. So these are the 4 smaller fragments, and they correspond to, each one of them corresponds to a different description logic. So OWL2 DL corresponds to what is called a Schroid T, and we looked at this briefly yesterday, right? So S stands for ALC plus transitivity. So it supports role transitivity and all the things that are part of the ALC description logic, which is the existentials, universals, and then the union and so on. R here stands for the role hierarchies and role chains. And so you can have sub roles and the uncle kind of relationships. O stands for nominals. That means you can come up with these enumerations and closed classes. I is the inverse roles, and Q is the qualified cardinality restriction. So you can have these cardinality restrictions as well. D here is the data type. So Schroid D has a very high reasoning complexity. So that's the double exponential non-deterministic time complexity, right? So that, which is not practical. So so OWL2EL, the other 3 fragments, OWL2EL, QL, RL, they all have polynomial time complexity. But so that obviously means that the expressivity is lower than OWL2DL. But for many use cases, this is already sufficient, right? So OWL2EL, for example, is used extensively in the biomedical domain, and there are very large ontologies that use these OWL2EL, and it is sufficient for their use, right? So and these 3 are called, that's why they are called the tractable profiles, because the reasoning time complexity is polynomial, but for OWL2DL it's exponential. So so in most use cases we generally stick to one of these 3, and they vary in terms of the constructs they support, right? So for example, existential is supported here, but it may not be supported in one of these 2. But there is some overlap. There is definitely an overlap between these 3, but there are also obviously certain differences in terms of the constructs that they support. Okay. And there's also the purpose. So for example, OWL2EL is used in when you have lots of classes and properties. OWL2RL is generally used when we have to define our rules, right? So it is generally, R here is meant for rules. So if we have to come up with our own rule-based custom rules, then you can go ahead with RL. Q here stands for querying. So the main purpose is to query the applications, and that has to be efficient, then we can go for this. And this is used in, like, for example, SNOMED is a very popular biomedical ontology, which is very large. So if there are a large number of classes and properties, you can go ahead with OWL2EL. Okay, so this is the overlap, right? So there is definitely an overlap, like I said, between these 3, RL, QL, and DL, but there are also obviously constructs that are sort of distinct for each particular profile. Okay, so yeah, this is the sort of the summary in terms of the complexity. Summary slide. Okay, so that's it.
Is there so how do they prove undesirability of OWL2? Because you don't have any variables, no? So it's a like what kind of problem do they use to show undesirability of OWL2?
What
Yeah,
kind of
yeah.
problem?
Like
Problem that-
like they have to have some reduction, no? Like either from some tiling
So,
problem.
so generally these complexities with respect to reasoning time. So let's say,
Okay.
um, so again, so let's say in OWL 2L you have A subclass of B and B subclass of C, then so you can infer that A is subclass of C, right? So, but that is for
Okay.
one axiom. But if you have all these constructs put together, then what would be the complete reasoning time? So, so these are generally the reasoning complexity. So even
Okay.
this one is with respect to the reasoning.
Okay. Yeah, no, I was just asking about, like if you want to show something is undecidable, you have to show that some already undecidable problem, you can reduce.
Ah, I see, I see, I see. Okay, okay,
I was asking like what is the reduction
okay,
range? Yeah.
okay, okay. So this is the so this is the satisfiability. We can let's say in
Yeah, satisfiability of
app-
FO2, FO is undecidable,
right.
but all for that you will have arbitrary quantifiers and variables and all these things. And yeah, but we don't have all that. We have very limited um,
So,
exclusive
so for
in
example, like while
mechanical.
building the tableau, so we build tableaus here as well to prove the yeah, the validity or the satisfiability of these the knowledge base. So it's similar. So it's similar to the tableaus that are constructed in first order logic.
Okay.
So in that sense, yeah. So for example, whenever you have a there exists, you can, or it is required that you introduce a new variable. I don't know, is that
Okay.
that answer your question?
Yeah.
Okay. Oh, yeah, okay. So these are some references which and I can, like I said, I can share the slides and more. If you're interested in learning more, you can definitely go over. Okay, so this is sort of the we can now take a break. So this is about how to. So we, like I said, so we discussed about description logics and how to comes from description logics. And now using how to, we can construct these ontologies. So that's what I'm going to discuss next on how to use these this OWL language to construct ontologies, right? So before I move ahead, I thought I'll just briefly discuss what an ontology is. Um, so maybe I can discuss this part and then we can take a break, right? We can take, I don't know, what, a 5 minutes break or something. And so
No,
if you
when we take a break, usually we take 15 minutes break.
okay, sure, yeah, we can take a 15 minutes break. And um, so in that break, during that break, if you want to, you can install this protege. I can give you the link, and some of you can install it. And if you want to follow along, we can also do that. Or I can build it and you can just look at how it is built.
Yeah.
Also, right? So whatever. So let me I'll go over the brief introduction of ontologies and then we can take the break.
All right.
Is that okay? Yeah, okay. Okay, so using this language called OWL, and OWL 2 is just the next version, right? So it started with OWL 1 and OWL 2 is the next version. So that's why we call it as OWL. But OWL is a language that can be used to construct these ontologies. So then the question is, okay, what is an ontology, right? And that's why so I'll briefly discuss what an ontology is, and then we can construct that ontology. Okay, so ontology has it's a very old term and it has its origins in philosophy, and it dates back to several centuries. So there are philosophers like Socrates, Plato, and so on, and those were the ones that came up with these ontologies, and they used to have discussions on about different types of different ontologies in the world. So okay, what is meant by ontologies? Just that it's a discussion of how things exist, how do you categorize them, and so on, right? So for example, if there is something like a table is, so now how do you describe table, right? So you may want to start by categorizing it, saying that, okay, table is a type of furniture, table is something that has 4 legs, and so on, right? So, and then you can also put it in terms of the context with the surrounding things. So let's say other related things. So table is in a part of a room or an office, and so on, right? So you can discuss this. So you discuss how things exist, and in general about their existence. So that's the general definition of an ontology. So we use the same thing in computer science as well, but with a little difference, right? So we'll talk about that in the next few slides. So we generally discuss these things. So let's say whenever uh, we want to know about what an ontology. So let's say if we categorize it, and then we discuss what is it made of and what are the related things. So that is all what an ontology is. So in the CS, okay, these are more formal definitions. But we can take a look at one of them and then sort of skip it, right? So an ontology is formal, explicit specification of a shared conceptualization. So that means, so generally ontologies are built in a group. So people, let's say domain experts come together, and let's say if I'm an ontology engineer, I also sit with the application developer. So let's say there's someone who wants to build a recommendation system on top of some data set, right? Now they need the definition of some of the domain knowledge. Let's say these about healthcare. So then you want to sit with the doctor, let's say someone like a pediatrician or a cancer specialist or someone, and then get to know more about the domain. So it is shared because at least this group agrees with the vocabulary that we are using. So these vocabulary consists of the important classes, the properties, and the relationships between them, right? So that's the shared part as well as the specification part. So in the specification, you give out what are all the different concept relations and how are they related to each other. And it is the formal because it is based on a formal language like first order logic, right? So that's why it's formal. And it is shared, like I said, because it's a group of people, at least they agree. So it need not be the case that others agree, but at least this group should agree. And ontologies provide an abstract view of the domain, which, okay, so I'll also talk about this a little later when we have these diagrams, right? So using these diagrams, you can quickly know about the domain. Okay. So there are a couple of other definitions, but it means the same thing, right? So this is a slightly, okay, it's a another definition. An ontology is shared understanding of some domain of interest. So it is shared because, again, a group of people come together and they put together this ontology. It is generally the case that even others, since they are domain experts and people take good care while building the ontology, even others find it useful and then they tend to reuse it. Okay. But the biggest difference between ontology and, let's say, some of the other conceptual modeling techniques, let's say like UML, ER diagrams, and so on, is that this is machine processable. So we already saw the syntax, right? So the syntax, if using that syntax, if we can build an ontology, then machine can also process it and use it. Okay, so this is just an example. I quickly go over it. Sorry.
When you say there cannot be a big ontology of something, like, is it a mathematical impossibility or it's a practical difficulty?
Okay, so when I say that there cannot be a big ontology, right? Is that oh, this one? Okay, yeah. No, that's not mathematical. It's just practically not a good idea, like, because so this is time taking and expensive also, because if you want to engage with the domain expert, it will be an expensive process, right? They'll charge per hour or whatever. They'll have some limitations in terms of the amount of time that they can spend, and also the yeah, in terms of, let's say, their availability also. So now,
So then how will they build semantic web?
okay, so generally it is made up of these smaller pieces of ontology. So let's say if we go back to the university example, maybe our group will build the will build about the courses, the faculty, and the registration process, the course registration. Maybe somebody else can build an ontology on the administrative from the administrative perspective, right? So admissions and also maybe someone else can come in and then they can talk about the policies, what should be the different policies, and someone else can come in and build about the let's say the cafeteria and then the facilities part of it. So so all these things can come together and then it can work together, right? But one
Okay.
one group building a very big ontology is not generally it's time taking and it's also expensive. So you need to retain the same group for a longer amount of time, which is hard.
Right. It's kind of.
Okay. Okay. So generally, so let's say if you ask two groups to build an ontology on the same domain, they end up looking at it from different perspectives. Right? They build an ontology based on their perspective. So if I just give a very broad statement that I ask one of you to build a ontology on the university, and also the other person to build an ontology on the university. Let's say I also build an ontology on the university. I may look at it from a different perspective. Let's say I may be interested only in the courses and the course registration part. Maybe somebody else might be interested in the departments. Right? Like this university has, let's say, 5 departments, and the way it is structured, like how is the so there are deans, there is a director, and so on. Right? So they may be focusing on the organization structure. So each one will have their own perspectives, and there is no right or wrong perspective, except that there is a way to scope the entire thing. We will come to how to scope it right later on. But yeah, this is just meant to show that there are different perspectives. So I give some examples. So let's say if this picture is shown to all of us, we'll have different perspectives of it. So we can talk about it from the cuisine point of view, or if someone is interested in cooking, so they may be thinking of the recipes that go into it and the cooking utensils that are required. And if somebody is taking care of the calories that are going in, then they may be looking at it from the calories point of view. How many calories am I taking in, and so on. So if you ask these three groups to build an ontology, they will be building it according to their perspective. And there could be some common concepts and relations, but it will be can be totally be different, right? So that's why there is a need to scope it. And like I said, we'll come back in a few minutes on how to scope those things. Okay, so this is just a again I put together a summary slide on the definitions, but we discussed what the definition is, right? So we can move on. And there are other ways to ontologies is just one way to obviously model the world. There are other ways to do it, but one of the main differences is that ontologies are machine processable and you can infer based on them. And then the second is you can also put in these complex relationships. So for example, in ER diagrams, a relationship cannot stand by itself, right? But in ontologies, you can create a role or a property called has son, and that's it. You don't even need to say that has son is related to a person, or it can stand by itself. So that's another difference between ontologies and others. So I'm going to skip over these explicit differences, but these are the two important ones. One is that it's machine processable, then you can have complex relationships, and it can be used for inference. But again, each one has its own advantages, right? So for example, in UML diagram, you can show the flow of activities and code, the way the activities flow around, which is hard to do in ontologies. Okay, so depending on the scenario that you want to model, you have to pick the right techniques to use. So that's the takeaway. Okay. So again, there are, in terms of the definition, the high level definition in ontologies, in philosophy and CS it's the same, but there are some minor differences, right? Or minor, or in some cases it's major as well. So I put together these differences. So for example, in philosophy, it is generally used for debate among the people. They want to discuss and then debate about certain things, and then that's why ontologies were helpful to just categorize and then know about their existence. But here we generally see computer science, we have specific applications that are built on top of these ontologies, and that make use of these ontologies. Yeah, and this is in natural language, and this is obviously in a formal language, like description language, right? Okay, so we'll not be discussing too much about these knowledge graphs, but I'll just give a brief sort of a description, and then we can move along. So in ontologies, we generally capture the schema knowledge, the abstract level knowledge. So that means you say that faculty works at IIIT-Delhi, right? But in knowledge graphs, you capture the instance data and how they are connected to each other. So you say that Raghava works at IIIT-Delhi. So Raghava becomes one node, IIIT-Delhi becomes the other node, and work set is the relation that connects these two nodes. Right? So that's the knowledge graph. But there is obviously a connection between knowledge graph and ontologies, because you can have this type information. Now you can say that Raghava is a type of faculty, IIIT-Delhi is a type of university. So there is a connection between instance data and the schema knowledge. And it's the same here, right? So you can say that Da Vinci is a type of painter, Italy is a type of country, and Da Vinci belongs to Italy, and so on. So I'm going to skip over this one. Yeah, this is, and we can come here. Okay, so what's the point of building these ontologies? Right, so one is that you want to, okay, so generally it is the case that when you build an application, right, so you are building a whatever, a question answer system or a recommendation system, all the, apart from the application specific logic, you also have the domain information somewhere. You need to make certain assumptions about the domain. Let's say the domain could be e-commerce, right? So let's say you're building some sort of question answering system for something like Amazon or eBay or Flipkart and so on, right? So you type in a question, and then let's say you're looking for a television, and all the televisions which satisfy that criteria should show up. So now for whatever is the domain, you are making certain assumptions, and there's also this recommendation where let's say if you are looking for a TV, then it shows up when you're buying something. It says that okay, people have also looked for the TV stand, or they may have looked for what is it called, a music system, or a sound system, right? So it can make these recommendations based on whatever you are browsing or purchasing. So that means there is a connection between these different things, right? So there's a connection between TV and TV stand, and TV and sound system, and so on. So either that is implicit, that is hidden inside the application logic, or you can bring it out, right? So ontology is a way to bring it out so that it can be used by other applications as well. So now if you put this out somewhere saying that there's a connection between TV and TV stand, you can use it, you can reuse that knowledge even in other applications, right? So question answering system is one application that is making use of this knowledge. Maybe you can also build a recommendation system or a chat bot that can also make use of this knowledge. So that's one advantage of it. So you're sort of making this knowledge explicit, and you're taking it outside of the application. Okay, so that's one. And now if you do that, you can exchange it. So you can also exchange, other applications can also start using it. Okay, so that's one advantage. And then the other advantage is that okay, you can, when we, since it makes use of formal languages, you can, it can be unambiguous. So you can, when you state that car has exactly one engine, there is no ambiguity in it, right? So that's the other part of it. And the other advantage is that you can start making these inferences. So let's say you have only these two facts, then you can infer that penguin can also fly. And later on, someone added this fact that penguins cannot fly. Then it can detect, the reasoner can detect that there is some inconsistency here. So you said that all birds fly, penguin is a bird, and then you add, later on someone added that penguins cannot fly. So there is some inconsistency, and you may have to handle this. So how to handle is up to the ontology developer, but it can at least detect that there is some inconsistency here. Right, so that's the other advantage. You keep adding facts to this knowledge base, and if it becomes inconsistent, you can know. So the other advantage, third advantage, is that you can get a quick overview of the domain. So let's say you are a new member in a team, right? So there's a team in, I don't know, some, say Microsoft or some company, and you are a new member, and you are asked to go over these CSV files. This is a snippet from a CSV file, and it has only these numbers. So the other team members, they are familiar with these files because they have been working on, spending some time with it already, and they have interacted with the domain expert. So let's say this is a file that comes from the meteorology department or something like that, right? Where you have lots of numbers. Some of them have columns, some of them don't have any columns at all. But if you sit with the domain expert and person who is in charge of these applications, where the data comes from, then maybe that person can help you understand what this data is. But instead of, okay, but if for a new member to come in and quickly understand, it will again take time, right? They will have to either interact with the domain expert again or with their team members and so on. But if you have an ontology, it's like a documentation. So you can have this high level information. So I gave this example from the students and teachers and courses, right? So you can have these circles are the concepts, the relationships are the edges here, and these are the literals, the data types. Right? So you can take a look at this, and it's a lot more easier and quicker to get to know about the domain by looking at this ontology. So that's the other advantage. So it can also be useful as a documentation for the domain. Okay. And
So
yeah.
this web picture you have shown, is it some in some language, or there's some?
Yes, yes.
Some
So
standard
later on,
format?
when we build an ontology, we can also get this picture.
Okay.
So we'll be building an ontology using a tool, and we can visualize that in this way.
All right.
Okay. So the other important thing is other modeling techniques. These are declarative. So you can, if you are going to implement the domain knowledge in a certain way, you can do it in any language of your choice, right? So for example, you can use Java or Python or whatever, but you only specify the relationships in this abstract language, and then the implementation can happen in any other language. Okay, so that's about the ontologies. So now we can get started with the designing part, and we can come back after the break. So let me, so I don't know if, so I'll just put the link to this one in the chat.
Yeah, I already downloaded and installed.
Oh,
I think
you
everybody,
already got it. Okay.
yeah, I think Vinod
else
and
is
Saina
here?
also should have installed it. Yeah.
Okay, great.
Yeah, I've also installed.
Yeah, the web property.
Yeah,
be
protein.
sufficient enough, right? Yeah, the web
Right.
property
Yeah.
should be
All right.
sufficient, right?
Yeah. So what time should we join back again?
Up to you.
11:30.
Okay, sure. Yeah, we can join at 11. Come back at 11:30, and so I'll bring up the protege, and
All right.
we can meet again at 11.
All right. Let's meet at 11:30.
Sure, sure.
Yeah.
Are all of you at IIT Goa, or how is it? Do you know? We know
I am
that.
IIT Goa. Saina is my PhD student.
Ah.
And we know this is an independent researcher. He is based in Chennai. Yeah.
Okay. So you are not. You don't know Vinod earlier, is it, or you already know him?
No, I know Vinod. I know Vinod. We have
So
met
you know.
many times.
Yeah, I know Amal from CMI, from my
Okay.
CMI.
Okay. Okay. Nice. Yeah. Okay. So I guess we can get started. So I also started this protege in the meanwhile. So I don't. So we can do it either way. So we can either. So I'll go along. I'll take your suggestions and build it, or you can also open it and then build it along with me. Whatever works for you. So, but before we get there, I'll briefly discuss the steps, and then we can get started. Okay. So should we start the recording?
Started already.
Oh, it's already started. Okay, great. Okay, so okay, let me just go over the steps, and then we can get to the building ontology building part. Okay, the first thing to remember is that okay, it's a group activity in the sense that you have a domain expert, the ontology engineer, and then the application developer, right? And there can be more than one person in these roles, right? So there can be one or two domain experts or more domain experts. There can be a couple of ontology engineers, and then there are these application developers, and they'll have to discuss and then come up with the vocabulary that they think is right for this for describing the domain. So so from that point of view, it's their view of the world. By world we mean the domain, right? So there's no one correct way to model the domain. So some of them could be interested in one part of the domain. The others, if there's a different group, they could be interested in a different part of the domain. So it is okay to. That's why we say that there's no one correct way, and it's also an iterative process in the sense that it's not, you don't build it and just leave it up, because later on when there are new requirements or other features that get added to the application, we may have to come back and change the ontology, which is okay. And generally you keep discussing these changes with the domain expert and then keep making changes, right? Um, so that's why it's an iterative process. So now so how do we get started, right? So the first thing that we have to do is to fix the scope. And for fixing the scope, we have to come up with a certain set of questions that the ontology should answer. So let's say if it is about the transportation domain, so so we'll have to figure out questions such as that are related to, or if it's related to the movie industry, then we'll have to ask questions such as, okay, who's the give the list of all the movies by a particular actor, right? Or you can say that, or you can ask question that give me a list of all the movies that have X as the director and Y as the producer and so on, right? Or Y as the actor. Um, or maybe you can say given two movies who are all the common actors and other crew members who worked on these two movies. So these are different types of questions that we can use, and they generally restrict the scope of the domain. So because that's important, right? Each domain is very vast, and we cannot model everything in that particular domain. So now that you have limited the scope, the next step is to come up with some initial set of concepts and properties. And for that, we generally use the nouns. While talking with the domain expert or while reading something, we can pick up all the nouns and the verbs. So nouns generally become the concepts, and verbs are the properties, right? So and then okay, we already briefly discussed, okay, how do we determine the scope and restrict the scope. So we'll have to ask these questions, which are called as competency questions. So, what are the questions that the ontology should answer, and then other things such as how will the ontology be maintained, who maintains it, how will it be updated, and so on. and what are all the different applications that can possibly use this ontology. So these are all the different things that can be used to, it's like the metadata, right? So um, it is like an artifact that needs to be taken care of during its life cycle. So we'll have to also, so generally these are also discussed. Okay. So I take the example of cooking recipe here, but we can work with other ontologies as well, right? So when we start building an ontology, we can discuss other domains as well. So in the cooking recipes, um, um, so the idea is that there are multiple websites that have these cooking recipes. So can we bring them all together into one place? Okay, so one of the first steps is to have these build a set of competency questions. So these need not be very exhaustive. So it can be a small set, right? Let's say five competency questions or 10 competency questions that the ontology should definitely answer. But beyond this, there can be more questions that the ontology can answer. But these are the questions that the ontology should definitely answer, right? And so while building the ontology and later on after the ontology is built, this acts as the test, the litmus test, so that to verify whether the ontology is at least answering all the questions that we initially set out for the ontology.
Can you give some examples of?
Yeah, right. So, for example, from the cooking recipes point of view, it's something like retrieving the cooking instructions, right? The recipe instructions. So, for example, what is the recipe for paneer tikka masala? Or if you are in a hurry, so then we can figure out all the. Let's say we can say that give me a list of all the dishes that can be cooked in under 30 minutes using some fixed ingredients. So let's say I have only tomatoes and potatoes with me. So I'll say, okay, give me a recipe that that uses only tomatoes and potatoes, and it can be made in under 30 minutes. So that's one question that you want the ontology should answer. Or it could be based on the cooking utensils. So let's say you want to make use of only the microwave, right? And so then you can ask for, okay, give me all the recipes that make use of microwave and nothing else, right? So something like that. So these are all the questions, some possible questions that you can answer. You can ask the ontology. And like I said, in the movie domain, we can have competency questions such as give me a list of all the movies that an actor X and Y have acted in, or give me a list of all the questions that are below certain budget. Let's say I don't know, like 2 crores budget, or that were shot in some locations. Give me a list of the movies that were shot in Kodaikanal or something. And so those are some potential competency questions. So based on those questions, you can now restrict the scope, right? So you look at the concepts and properties that can help in answering these questions. So it can answer more questions, but it should definitely answer these questions at least. So that's a way to restrict the scope. Okay. So so I think we can so this is an important aspect, but we'll not be reusing any. So one of the important things is to generally reuse as many ontologies as possible. So let's say when we are building an ontology for the movies, maybe there'll be other ontologies that already have defined what an actor is or what a director is, right? So we can import those, at least the subsets of those ontologies, and then reuse them, because someone has already built it. So it's a way to quickly get started and save some time, right? So that's why it's important to reuse as many ontologies as possible. And in order to know what are the existing ontologies, we need to have a repository, right? So these are some of the popular repositories. There's bioportal for all the biomedical ontologies. We haven't discussed what an ontology design pattern is, but it's very similar to software design pattern, where it tries to solve or answer a particular design related question, right? So it's a smaller ontology. Design pattern is also an ontology, but it's much smaller, and it will only answer one specific design question. So something like how do you model a trajectory, right? So trajectory can be can come up in multiple situations. So there is a trajectory that a flight takes from, if a flight is going from X to Y, follows a particular trajectory. Say there's a trajectory that for example, a cruise takes. There's also a trajectory that comes up when birds migrate. So birds migrate from place X to place Y, and then they follow a certain trajectory. Now, how do you model such trajectories? And again, there are multiple other domains also, right? So generally, these design issues they are across multiple domains. So there's a trajectory that a rocket takes, and so on. So this particular design pattern, the trajectory pattern, tries to model the trajectory design use case. So now you can start using this wherever you find trajectory, right? So you don't have to sort of reinvent the wheel. Okay, but at least in our case, when we are modeling an ontology, we will not reuse any existing ontologies, because we can, that allows us to build it from scratch, right? So it will be good for the example, as an example. Okay, so we'll now switch over to the protege, and then so this is the starting screen that we come across. So the first thing that we should generally do is fix this or change this IRA. So this is the default IRA, but we should change it to the way that is to something that is suitable for us. So let's say it's a good idea to start with the domain, whatever sorry, the organization's domain, right? So because that will give you a unique IRA. So for example, in my case, it will be IIIT.edu.in, and then let's say we can have this ISLA, maybe summer school, and whatever is the domain. So let us pick a domain first. So what would be your suggestions for a domain? So which domain should we model? So it can be I don't know, anything like something that all of us can easily comment and come up with some concepts and relations. Let's say like movie, sports. Within sports, you can pick some specific sport, transport, university, and so on. So whatever you find interesting, we can pick. So which one do you suggest?
Movie.
Okay, yeah, we can stick to the movie domain, right? Okay, so then let's, for example, we can say movie, and then so this becomes our IRA. And now IRAs are, as we discussed earlier, right? So each concept and property is given an IRA to uniquely identify it. So we'll as we build,
It was URI, no? What is I in the beginning?
so IRI, I stands for internationalized resource
Okay.
identifier. U is the uniform resource identifier. So the difference between these two is the encoding scheme. So in IRIs, the encoding scheme is UTF-8, which has a higher sort of character set, right? So in URIs, it's the ASCII character set. So we cannot have something like the special characters like the umlaut and the accents in URIs. Okay, so now we switch to this entities tab. So if you want to import ontologies, this is the way to do it. So you can import existing ontologies into this particular ontology so that you can start reusing it. But here we will not be reusing any existing ontologies, right? So okay. So the first thing that we should do is, as I mentioned here as well, so you sit with the domain expert. So in this case, all of us are domain experts. We assume that all of us are domain experts because we have seen and lots of movies, I would hope. So we can list out the important terms in the domain. So terms could mean both the generally the nouns, the phrases, verbs. So it can be longer words as well. right? So they are useful for generating the classes and properties, right? And so we list out the terms, and let us also come up with some competency questions so that we can scope it, right?
Okay.
Okay, so okay, maybe. So what could be, what do you think are the popular or some of the important terms in the movie domain?
Name, I mean, title, release.
Title of the movie.
Yeah, title of the
Okay.
movie, release year.
So okay, so the
Yes.
movie itself. So let's say okay, movie title, right? So movie title.
Release year,
Okay.
then
Cast.
director, yeah,
Yeah.
cast, cast. So actors, yeah.
Okay, cast, actors.
Actor, then director,
Director, producer.
Yeah, director.
producer, cameraman, camera person. Sorry, it should be camera.
Cinematographer.
Cinematographer. Okay, so that's same as camera person, right? Or is it different?
Yeah, cinematographer is fine. Yeah.
Both the spelling is correct. Okay, and what about some, yeah, release year? Okay, these are all
Yeah, competency questions.
okay.
Show the
So I will say
films.
CQs.
Yeah, yeah. Like list all the films directed by a certain director. Movies directed by certain director, all movies
Similarly,
acted by a
particular
yeah,
actor.
all the movies acted by a actor after 2015 by an actor. The actor after 2015.
Maybe we can add this review things.
Yeah, yeah,
Okay,
yeah,
so movie review.
yeah,
And then also there can be a question on that as well, right? So
yeah.
this movies that
That have a high review rating.
review rating, right? Okay. A movie review can have a rating, and okay, maybe that's part of this one, right? So can have a rating, and it can have a the person who reviewed it, reviewer.
Yeah,
Kind of.
text review, review
Yeah,
text.
review. Yeah, review text, review body.
Yeah.
It's movies that
That,
that are
with a
above a
kind,
certain
yeah, rating.
rating. Could be all time. We can also include the time, the year, or you can just leave it. Okay, so we have now at least a few important terms and the CQs as well. So that allows us to restrict the scope, right? So for example, we are not talking of the movie making process. We don't talk about the budget, for example, here. We don't talk about the locations and all those things, right? Like there's also things about releasing it, distributors. There's also the role of distributors,
Yeah, yeah.
theaters, and all this. So there is a lot more things that we can definitely talk about in the movie domain. But but we are restricting the scope, and that's why it's important to have these sequences. Okay, so now that we have done this, we can start putting in these terms in the ontology. So under entities, we have all these different. So we have classes, object properties, data properties, individuals. Right? So these are the important ones. And like I said yesterday, this is the top concept. That means it's the class of all classes. So this is the parent class for all classes. These like these equivalent to mu in the sets, right? So this is a set of all sets, or like these like the God concept where it's like the super class for all classes. So you start here, and then we can either right click add a subclass, or we can also click on this one and it will add a subclass. So we start with, for example, movie. Now this will automatically take in the IRI that we already defined, right? So this is the IRI that we defined. Okay, we can also put in ontology somewhere, but yeah. So this is the first concept that we created. So now we can go ahead and create other concepts and properties. And by after we build the ontology, we can figure out whether these questions are satisfied or not. Okay. So movie will have movie title, the and release year, right? So these are like the properties. So we can go to either object properties or data properties depending on what they are trying to connect. So if it's a movie title, so it will connect a specific movie with a string with the name of that movie, right? So this is a data property. This also happens to a data property. So release year is again connecting the movie with a specific number. So both are data properties. So we can go to the data properties section, and then we can start creating the properties. So first one is movie title. So I create that. So whenever we create it, it's a good idea to put in the domain and range as well. Right? So the domain of movie title would be the movie, and the range would be one of the data types. Right? So it could be it should be a string. So let us look for a string, and then I added that. So I haven't yet saved it. So let me just save it. And these are the different what is it? The serialization formats that are available. So and all of them are, among them, the most human friendly is the functional syntax, which is what I used in the how-to slides. Right? So we can stick to that one, but we can also choose other variants. Okay, so okay, where do we save? So okay, we have to pick up some place to save. So let me do it. So I'll try to save it along with the slides. So the default extension will be OWL. So it will be saved as movie-ontology.owl. Right. Okay. So we are done with the title, and now we can construct the one more property, which is the release year. So release year will also have the domain as the movie, and the range would be an integer. Right? So there is the actor, director, producer, cinematographer. So all these are, so we can construct all this. So there's this bottom-up approach and top-down approach. So in the top-down approach, you sort of start with the more general classes, and then keep adding these more specialized classes as a child, right? And in the bottom up, you do the opposite. You start with the more specialized classes, and then you build up to the parent. We can also follow the mixed approach where we do a bit of both, right? So there is something that is common between all of them, right? So there is actor, director, producer, cinematographer. All these are, we can say, they are like members of the movie making process. So it's like the crew member. So if you want to have a common parent, we can create something like a crew member, and then make all of them as subclasses of the crew member. Does that sound good?
Yeah.
So let's go ahead and create this crew member. So the other thing, generally, that I recommend is we should either stick to singular or plural, right? So we can either, so if we can either say movies or movie, crew members or crew member, but it should be consistent, right? So I generally stick to singular case, like, so make it all everything as singular. Okay, crew
Yeah,
member.
so I have a doubt. So here we are actually defining movie title, crew member, everything as a relation. Yeah.
No,
what
so
will be
crew
the
member is a class.
crew member is a class? Yeah. Okay. Crew member is a
Data
class, but yeah, these are data properties. These are relations.
Right.
And so when we talk about movie, what are we intending to be the name? I mean, like the movie property has the domain movie. So what is going to be that? Like as is
No,
going to be a
movie title.
unique identifier. Yeah.
So movie
So
title
domain is a
will
movie.
have the domain movie.
Movie title will be a string. So what will be movie? It will be a number or some identifier which we will assign for every movie.
Okay. Right. Okay, I got it. Okay. So yeah, generally we can either have something like an identifier, or we can even say okay, like Titanic, right? So Titanic, we can even create an instance like Titanic movie.
Okay.
And have the string Titanic as a name. Or we can say, okay, movie 3450,
Okay.
which is the ID, and then
Okay.
that
Yeah,
can
so it
have,
will be a unique ID because there could be many movies with the same name and so on. Yeah. So
right. Yeah.
okay.
Okay, so crew member. Now we can create subclasses for this one. So let's say actor is one subclass, right? And we have director and producer also, right? So director, producer. We also had cinematographer. So I guess these are the 4, and we have the movie review. Okay, so we can create that as a right. So now at the high level, we created 3 classes, and crew member has some subclasses as well. Right. So this already this has come up here. So now movie review, there are some properties associated with it, right? Like the rating, reviewer, and review text. So let's go ahead and create the properties. So we'll have to figure out whether they are object properties or data properties. So rating is again, it connects the movie to some number, right? Reviewer, it's not. So okay, we can have a reviewer. Should we create a we need to create a class called reviewer, right? So reviewer can also have a hierarchy, because reviewer can be a person and reviewer can be a subclass of person, or we can directly go ahead and create reviewer as well. Either way is okay. Okay, but just to demonstrate, maybe we can have a person, and person can have a subclass called the reviewer. So whenever like I said earlier, so in this, at least in this case, we are not reusing existing ontologies, but say some of these things are pretty common, right? So for example, you can find person in other ontologies as well. So we can import. So instead of creating our own person, so this is now a person that belongs to this particular IRI, right? So instead of that, we can import, and we can have the person from some other ontology, and then extend that with the reviewer class, which belongs to our ontology. So in that case, we are not creating one more person, and instead of that, we are reusing existing person from an ontology. Okay. So reviewer thing has this property connects the movie with the reviewer, right? So this is an object property. So we can create this something like let's say has movie reviewer, so that it's descriptive. So has movie reviewer would have domain as a movie, and range would be, so this is what I was talking about earlier. So if you have two different ranges, right, so then it will be treated as an intersection. So you will have to be careful. If you meant it as, if you want it as intersection, you can do it, but if you want it as some other relation between all these ranges, then you should explicitly state that. So in this case, the range would be the reviewer. So we'll go ahead and paste that. Okay, so we can also check whether any of these properties or characteristics hold. Okay, starting with the functional. So if A has reviewer B and A has reviewer C, then it need not be the case that B is equivalent to C, right? Because there can be more than more than one reviewer for a movie.
Yeah, it is asymmetric, reflexive.
Right. Asymmetric and reflexive. Right. So we just have to tick mark it because we have this nice interface, right? So later on, I can open the ontology file in a text editor, and then I can show you the syntax that it follows, right? So it will be similar to the one that we looked at in the slides. Okay, so the other one is review text. These again a data property because it connects the movie to the. Oh, we could have actually. Did we have a review class? Yeah, we have a review class. Okay.
So in this
Oh, but
case,
then, yeah, right. Has movie review, so it has to
who
have.
review text has to be associated with movie as well as the reviewer, right?
Right. So, movie has a reviewer, and then we'll have to associate this with the review.
Yeah, so it makes sense to associate movie with the review, no? Review
True,
as a review as a class.
Right. So movie should be associated with the movie review, and then the
Rest should be object properties of the review.
true. So movie has movie review. So I'll delete this. We use this to delete. Movie has, yeah, this should be the one. So movie has what is the name of? Oh, we need to change this one as well. So the way to change it is, I think, so there's a way to, oh yeah, refactor. So you can rename it. I'm going to say has movie has movie review, which is a movie review. Oh, I should have. Okay, so now the domain of movie review is movie, and the range of has movie review is a movie review. Now this movie review should have a reviewer and review text and so on.
Yeah.
So we can associate that.
So the instance of this movie review class will be like reviewer rating and all those things. Are those the instance of the movie review class? Like
Okay, again, movie review class, we can create some. We can, let's say, create with some ID, right? So we can say movie review 1, 2, 3, 4.
Yeah.
And now that will have a review body and rating. And that movie review 1, 2, 3, 4 connects, let's say, movie 1, 2, 3, 4 with the actual review. Okay, so let's go ahead and create these three as well. Rating, the rating, I think we should go here.
We can make this rating to be this, have this cardinality property, right? Like maybe 1, 2, 3, 4, 5, something finite values.
No, but for each review, there will only be one rating, isn't it?
Yeah, but rating is a subclass inside movie review, right? Or is it
Rating,
not?
rating would be more of a property, isn't it? So review will have a rating associated with it, and rating can be the range of the rating can be an integer or a floating point number, saying that okay, it's 3.5 or 4.2 or something,
Mhm.
right? Isn't it? So, for example, like we can have as movie rating. Um, so domain is the movie review. Movie review has movie rating, and okay, range can be the any, yeah, double or floating point number or something. Right? Okay, so we have the movie rating. So what about the text? So we'll also associate the reviewer. I think we are done with reviewer. I don't know. Okay, we didn't yet do this. Okay, let's complete review text and then come back to reviewer.
Okay.
As so we can keep it descriptive. We can say has movie review text.
Okay.
So has movie review text will again, so a review
Movie review and a
will
review
have
text.
we
Yeah.
will have
Okay.
review text. So this is the string. Sorry, string. So the one that we are yet to put in is the reviewer.
Yeah.
As reviewer. Okay, so um, movie review will have a reviewer. Yeah, this is so reviewer can have again things
ID.
associated with the reviewer, like let's say name,
Yeah.
the organization to which the reviewer is, or it could be also independent reviewer, but maybe also associated with some organization, and the ID and so
Yeah.
on, right? The experience that the reviewer has and so on. Okay, so we put in at least these concepts and properties in the ontology. Now the thing that we are yet to do is make the connections between these classes, right? So for example, there's a relationship between movie and actor, movie and director, movie and producer, which we haven't yet put in. So we can also put them in. And we can also say things like uh, let's say, okay, if we want producer and director to be disjoint, we can add that. So there should not be anything in common. So there cannot be same person cannot act as producer and director. They cannot have two roles, right? So if you want to enforce that, or if you want to put that constraint, we can do so. So let us add a few of these here, and so that we can connect them together, right? So let's say movie has uh, now we can make use of these quantifiers. So movie is something that has at least one actor, right? Or at least one crew member. So we can also put it at the top level. Movie will have at least one crew member. So we can start, click here, click on this subclass. Uh, I can try it. Okay, I don't. hard to drag it around. So okay, let me let's do this here. So now, okay. So we want to go for this object restriction. Oh, okay, finally. I'll try to expand this so that it becomes easier to see, but okay, I have trouble with my fine. So we want to say that movie is something that has at least one crew member, right? So we need to create, okay, we actually need to create a property called a crew member that connects movie and crew members. Okay. I don't, oh, let me create it here itself so that we don't need to close this and then reopen it. So I'm going to create a object property called as crew member. Right, so now movie, this is what I selected, has crew member, and these are all the different, so it has cardinalities and the two quantifiers. I'm going to select existential quantifier, and if you select cardinality, you can select the value here, right? So whether it's 1 2 3 4 or something, and then I'm going to select the crew member here. So this is going to show up, right? So movie, um, so this is the subset which subclass of which is not which is here, and there exists, for there exists you have some, right? So there exists has crew member, so there should be at least one crew member for each movie.
Yeah.
So we can also put in some additional constraints. So let's say director cannot be a cinematographer, so then we can put in disjoint with I'm going to say this. So director and cinematographer are disjoint with each other. So this shows up here as well. So cinematographer is also disjoint with director, right? So in general, as a general rule, we can go ahead and say that the siblings are disjoint with each other. But we'll have to be sometimes be careful. But in general, that works, right? Because the only thing that is generally in common is that they have a common parent. Otherwise they are generally considered to be disjoint, right? But there could be cases where that may not apply, so we'll have to be careful, but in general we can treat it as a rule of thumb and then go ahead and try to make it disjoint. Okay, so we have made it disjoint. We can also associate movie with the movie review, so we can say the same thing. We can say that okay, a movie is something that has at least one movie review, right? Um, so we can again create this, go here, pick this. So movie has movie review, at least one movie review, right? So I added that as well. And we can also say
We
that
need
movie
both,
review
has movie review and has reviewer. Do we need both? Because they're both related, right? I mean, one means the other is also there.
true. So now we can connect movie review with reviewer. So for example, we can say that so I clicked on which one? What is it? I clicked on movie review. So we can say that movie review has reviewer where is it? Review. So we are now connecting, or there we are establishing some relation between movie review and reviewer.
Okay. Can we say something like if and only if I mean that's
Yeah,
a
yeah.
movie
If
review,
and
if
only
and
if
only
the
if it is
bidirectional thing, right? So
yeah, yeah.
so A is subclass of B and B is also subclass of A. So that's the equivalent thing. Okay, for equivalence, what do we? Maybe I don't know, some sort of alias, uh, actor or
What is the problem?
so he asked for an example of equivalence. Um, so I was thinking of having some sort of alias, right? Like say if we have okay, something like camera person. Right? So if we have one more class, then we can say cinematographer is equivalent to camera person. That could be an example of if and only if. So where you have by implication. So that's the equivalence here.
Yeah.
Does that
Can't we do it with the reviewer thing?
reviewer?
No,
Okay, how do you suggest that we do with reviewer?
No, reviewer and review. We have these two different things, right? But they are the same thing. Like there cannot be a review without a reviewer.
Right.
And if a movie has a reviewer, there has to be a review. I mean, they are both equivalent. No?
like
Okay, reviewer. Yeah, I got. So yeah, we established in one direction. So movie review has reviewer. So you want it in the other direction also. So reviewer is someone who is associated with the review.
yeah.
Is it? So for example, okay, we can say reviewer has at least one movie review. Has movie review. Did we have movie review class? Such property.
Yeah, reviewer has one, at least one review, and a review has exactly one reviewer.
At least one. Okay, right. So we can check this. Okay, we do have a movie review, right? So yeah, reviewer has movie review that also works, and then the other way around. But yeah, I'm wondering how do you make this equivalent? So here we can add. So for example, we can say
Or maybe just a one-to-many relationship.
has movie review. That should work. Um, okay, what's the one-to-many relation? Like
One reviewer can have many
many
reviews,
reviews.
but a review can have only one reviewer. A
Right.
particular review can have only one review.
Right. Or unless it's a team, right? Team of people who are
Yeah.
reviewing together, then
Yeah,
we
that's
don't do.
another
But
level of complication. But
yeah. Reviewer can have. So that is captured here. At least one movie review. So it can have more than one movie reviews as well. Okay, is that so we can also create certain individuals, but okay, I don't. So we can, for example, create a closed class and then put in some of these individuals as part of that class, or we can keep it separate. Right? So for example, I think yesterday someone asked a question about having these CSV files and data, and so we can get the data in the form of CSV files and JSON files, and then map it to these concepts. So, for example, we can say that column 3 in the CSV file maps to reviewer, right? So we can have these columns, something like let's say movie ID, that is column 1, movie name, and column 2, and then a movie, I don't know, let's say actor and director, right? So, or maybe actors and directors or something. We will stick to one role. So actor, director, and now you can start this CSV file, you can start mapping it to the concept. So you can, for example, map movie ID to movie. So that means each row. So for example, if it has 101, let's say Titanic actor, I don't know this actor. Let's say I'll give actor underscore 101, and let's say it is director underscore 101. So we can now, these are like the instances, these are instances, and now we can, if we do the mapping, then we'll have the type information. So we are saying that movie ID, so it will end up creating something like this. 101 like has, sorry, instance of movie, right? And then you can have then if you map this to the movie, then you can say, let's say 101 has movie name. I don't know if that is the what. That's the movie title, right? So we use movie title. So let's say movie title Titanic. So this is how it will end up creating instances. So once we do the mapping, we can get these instances when we run the mapper tool. So you only need to specify the mapping part, and then once you run the tool, you can generate all these A-box axioms, right? So that's why these can be large in size. So knowledge graph can be very large, but the schema can be pretty small, right? So we have done, it's a pretty small schema, but it covers lots of different, it can answer lots of different questions, and it can already have a pretty large graph associated with it. So this CSV file can have, let's say, thousands of rows, and once you do the mapping, it can generate all these automatically. Right. Okay. So we can also quickly take a look at the.
So is there some human? Can you import this as a file, the schema which you have just generated?
Yeah, it is a file. I'm about to show that. So we can. I'll open it and then I'll show you. So this is actually a OWL file, and this is what gets generated in the backend. Okay. So we have all these declarations for classes. This was the syntax that I was showing in the slides earlier. Okay. So object properties, yeah, we put them as, some of them as reflexive asymmetric, right? And then the domain range. So everything is it is here. So this is about the movie rating. We have the domain power range and all this. So these are the classes. Actor is a subclass of crew member. Cinematographer is a subclass of crew member, and so on. So it also, this is the one of the axioms that we put in, that movie review should have at least has at least one has reviewer who is a reviewer, right? So and yeah, you can definitely import this into Protege, and there are libraries that can read in this .owl file, and it can process all these axioms. So that's an example. So there is also, within Protege, you can also run these reasoners. By default, we get a couple of reasoners, but we can also, there are mechanisms to add more reasoners as well. So for example, it's useful. Okay, I can show you one example of inconsistency, right? We already put in this one, director and cinematographer are disjoint with each other. So we can create an individual and say that that individual belongs to both the director class and its cinematographer class, and we can check if the reasoner detects that inconsistency. So for example, here we can create some actor and who is also a cinematographer or something. You can suggest some name, or I'll pick some, I don't know, like John, kind of random name. Okay, so let me just go ahead and pick John and say that John is of type class hierarchy. Remember, John is of type actor, right? I think we said director and cinematographer is joined. So let's say director, and I'll also add this that John is also a cinematographer. So there are two things now, and here we said that okay, director and cinematographer are disjoint with each other. So we can just check if reasoner can detect that. So we start the reasoner. Yeah, and it shows up that. Okay, so it says that the ontology is inconsistent. And we can, this is the explainability that I was talking about. So it's easy to, since it's based on first order logic, it's easy to explain the decision because it has followed a specific set of steps, right? So we can click on explain and it shows the explanation. So we said that John is of type cinematographer. We also said John is of type director, and we already stated that cinematographer is disjoint with director. So obviously, John cannot be both a cinematographer and a director, right? So that's the explanation that it has generated. So now we can, it's up to us on how to fix it. So we can either say that John is a director but not a cinematographer or something like that. Right? So it changes the color as well, just to highlight that there is some issue with these classes. I'm going to stop the reasoner. And maybe we can remove John from the as a cinematographer, right? So then it will work as expected. Okay. So that's a brief overview of how to build these ontologies using this tool called Practical. But there are libraries. So for example, you can uh, use this OWL API, and it's available in Java and Python. Uh, so yeah, this is the main one. So this, so we can use this library which is in Java to read and even manipulate or change the ontologies. But generally, if it's already made, then you simply have to read it. So we can use this library. There's also one in Python, which is called OWL Ready 2. So this is the Python version, right? So you can also use this to already do this. So if you are more into Python, you can use this to again read and write these ontologies. I think so. We went over all these steps while building the ontology. So we enumerate the important classes, terms, and there are these two approaches which I talked about. We create these properties and hierarchies, the class hierarchies. Then for each property, we need to check the characteristics, whether they are symmetric, asymmetric, transitive, and so on. And we can also check. We should add the domain and range. Wherever required, we create these instances, and yeah, so that is all. Okay, so any questions? So
Yeah. So how do we query answer?
okay, yeah, okay. Oh, and then the visualization. So I also wanted to show the visualization, right? So I'll show both of them. So this is sort of hidden. It's here. This is easy. Okay, so yeah, we can keep expanding this. Let's say whichever is the so each okay, maybe
in
this
this
is better.
visualization, only classes are shown, right? Like
So
classes
the
and the entries
properties are
represent
also
the
shown,
relation.
but you will have to hover over these relationships. Like it's sort of,
Okay,
so
but
this is the subclass where it is a thick line with this symbol, but the other
okay.
lines, these are not, this is like a specific relationship. So this is um, the existential relation between these two classes, and this is also the existential relation, I guess. There's one here. Um, Subclasses are also shown. Yeah, you are right. And this is the individual that connects these two.
So
So this is
instances will not
one.
be
Sorry, what's
like individuals will not be
this is the
shown
individual.
here.
John is the individual, right? So
Okay.
this is connected, and then you can hover over this one just to know the relationship between these two nodes. So this is the individual has individual. So this is one sort of the built-in mechanism to visualize, but there is also there are other tools, right? So there is something called Onto Viz. Sorry. Yes. Owl Viz, I guess. Owl Viz. Yes. Oh, yeah, I forgot. So where you can upload, so this is online. Yeah, WebVow, right? Okay, so WebVow. So you can either download it and set it up in your machine, or you can also upload it, and you can get uh, diagrams in this form where you have a circle and all these shapes, which is what I was using it in my slide. And
So
you,
this
one
is
of you,
this knowledge, the knowledge graph that you were talking about, or that is something else?
so we can, sorry, I didn't get the question. Can you repeat it?
Is this the knowledge graph that you
Ah,
are
okay,
talking about?
okay, okay. Yeah, it looks, it is in that form, right? Like the graph form. But generally, when we say knowledge graph, it's mostly for instance data. But it does look to be in the graph form where you have the circles and edges. So if you want to, we can also add our own ontology to it. We can visualize it, right? So for example, we can uh, where it talks here. This one. So we can add it, and yeah, this is, it will get visualized here in this form. Okay. Yeah, it also talks about the relationships and then the, yeah, asymmetric reflex. So yeah, it does capture quite a bit of information, and then there is that there is this existential relation between these two. And the data types are the literals, they are shown in square boxes, rectangles. So these are other visualization tool which is pretty popular. But if you want to stick to visualizations within the protege tool, then we have ontograph, and it can do this sort of visualization. Okay, so that's about visualization. And then querying, there are couple of ways. So there is a query language called Sparkle, which works on these knowledge graphs. So once you have, not this one. Yeah. So once you do the mapping, say that okay, 101 should be mapped to movie concept, Titanic should be mapped to the movie title, and so on. You can start querying this particular data. So here you can ask for all those things. Right? So Sparkle is very similar to SQL in terms of its syntax. So you can say select something like this. Say actor, and then movie where where you can say like, okay, movie, whatever. So instance of, so generally instance of is abbreviated to A.
Yeah, has crew member.
Right, right. So it is movie of type movie, and
Yeah.
then movie. Sorry, M. Yeah, has crew member, right? So has crew member.
Yeah.
Whatever, some C, let's say, and then C will have title, right? So I think movie has a, or movie has a title. I don't remember. Maybe M has sorry, movie title T. So you can now ask for okay, maybe C and T, maybe who are the crew members of a particular movie, and then you can get that. But for this, there are some intermediate steps. Right? So first, you need to do the mapping, convert this to this particular. You get the instance data, which is the A box, and then you, since you want to query it, you need to put it in some knowledge base or triple store. So something like there are tools like Apache, Jana, and what to so. So they can take in these things, and then you can query. You can send in your query. It's like a database management system, right? So except that this works for this particular knowledge bases. So you can put in this data into one of these databases, and then you can start write these queries on it.
Mhm. Mhm.
So yeah, so that's how we can query it.
So what are the common places where, because you see that this is somewhere between structured database. It's a more structured database, yeah?
Right, right. Yeah, this is structured data, right?
This is structured data.
Hmm.
And in fact, it is more structured than a relational database.
Yes, yes, right.
You have a
Because in relational databases, we cannot say the relation between two columns.
yes, yes.
But here that's the advantage. So we can say the relation between the columns
And then you can say like subset relations,
right, right,
composition, and all
right.
these things. Yeah. Okay. And yeah, so my question was like, so what are the usual situations where you would choose
So
this
so
over a database representation? Like can you give me, like you gave me one example, which is this medical thing.
hmm.
It made sense because
Okay. So in general, when we want to make any of these relationships to be explicit, right? So the advantage of having a graph form is that now you can make the relationship between these two explicit and put it as an edge. So even in let's say relational databases, we don't know how is a movie name related to actor, or how is a director related to a movie, and so on. So it is sitting in the head of the domain expert, but we'll just, the idea is to just bring out that knowledge into let's say as an external artifact and then reuse it. One of the very popular use cases is in data integration. So let's say you have data related to a movie. So there's one database or one set of CSV files that talk about the movie name and movie actors, right? The crew members. Maybe there's a different CSV file that talks about the movie name and then the budget that was used on it, and then the revenue that it generated. So these are two different uh, files, but they are related to each other, right? So if you want to integrate them, this is a good way to do it. So you build an ontology that can capture all these facts, all these relationships, and then you use this mapping to create the graph out of it. So now you have one big graph that can integrate both these data sets. Now on top of the graph, there are again popular, like there are lots of applications that can be built. There's recommendation systems, question answering systems, chatbots. All
That's
these can
what I
be.
was talking, like, what are the more popular ones which are built using this?
So generally, okay, so let's say most commercial enterprises these days, they have a knowledge graph. So let's say including Google, right? So whenever we search, there's a something that shows up on the right hand side, which is the panel. So let's say we search for Abdul Kalam. So this is the panel that shows up, and these are the things that are obtained from the graph, knowledge graph. You can browse through the graphs or traverse through the graph and get all these things. So let's say these are the books. So this is the entity in the graph. Abdul Kalam is one entity in the graph, and you can search through the graph and get related things. Right? Like things. Obviously, there are a lot of other people whom we search for, but these are the people that are related to this entity, because all these are either presidents or scientists which belong to the same country as Abdul Kalam. So it's easy to, so these are like the recommendations, right? So you can build these recommendations systems or like question answering systems. So let's say this allows us to ask some more complicated questions. I don't know if Google can answer this. Let's say who is the person, okay, or maybe I'll start with the person who is both a scientist as well as a president of India, right? So let's see. I don't. Okay, so it does. So it can answer because you have scientist as one of the concepts and president as one of the concepts, right? Now it has to figure out the intersection between these two. So unless you explicitly have this particular concept and these concepts, it's hard to get this answer. Or it, okay, even here you will still have to browse and figure out, but it's very close to the actual answer, right? In the sense that it's not as direct as the other question. Let's say, what is the age of? I don't know, let's say, it gives a direct answer. But for the other one, it gave the right links, but you still have to sort of click on them and figure out. It did not give a direct answer like this one. Yeah, so it's useful in data integration. Again, what?
So IMDb, Amazon, everybody has this.
Yeah, Amazon has it, eBay has it, IBM has it, and then Bing, all the knowledge, all the search engines. Bing has it, then Yahoo in the previous days, it also has it, and then GE. So I worked in GE before I moved here. So GE had an internal knowledge graph. Yeah, several. LinkedIn has it. LinkedIn has built a knowledge graph. So the expressivity varies, right? So some of them may not have a very expressive ontology behind them, and some of them may have it. But in general, it's the wider the domain is, it's harder to build a good ontology for it. Because again, because you can't sit with domain experts and then create these things manually, right? So it takes time. So some of them have very high level general ontologies, like okay, there is this ontology on name, place, thing kind of. So it only has a high level picture. Like it captures high level concepts.
Yeah, it's a good BTech project actually to use these things and build something for local.
Build an application, yes.
Yeah.
So there are these chatbots nowadays. Chatbots they do make use of knowledge graphs, and then there are these question answering systems, which again make use of question answering systems, meaning something like the Google thing, right? Like you put in the term and then it'll get translated to a query.
Uh-huh. All right, that's from my side.
Sure, sure. Any other questions before we wrap up?
Okay.
Okay.
There are no further questions. Thank you, Raghav. We meet tomorrow at 10 o'clock. Yeah.
No, I'm done with
You are done. It's only
yeah,
2
with my
All
first.
right, sorry. Yeah.
So,
Okay.
so
Yeah.
this is the last one, right? Mine, I think my course was the last one.
Yeah. So yeah, it was. Then let me say a few words. I mean, it was very informative. Yeah. So yeah. So let's. We should have a more. This is. I mean, I think this is a good opportunity for actually where logic is actually practically being used. Yeah.
Right. Yes.
So, and it's pretty relevant also, very relevant also.
True.
These things can actually be integrated to. We have a course here, logic and computer science.
Okay.
So where
Nice.
they learn conceptual logic, sort of logic, and so on. So actually, one of those these kind of things are can be used as hands-on
Right.
project for such courses.
Right. So in my course also, semantic web course, in the first 2 weeks, I start off with first order logic and then I move on to description logics and other things because it is the base. So
But when you teach that logic course, it seems very up in the sky and not connected to the well
Right.
at all. And one of the problems is that most of this artificial intelligence course and machine learning course we have here, they have completely moved away from this logic and planning aspect. They have
Right. Yeah. Now they're many of them focus on the learning.
learning and so on. So people also have very little appreciation of these kind of techniques.
Right.
What do you think? I mean, that's a question which I also have I'm very puzzled about. So because Google on the other side is doing the exact opposite thing. I'll stop probably the video and ask you.
Sure. And I'll also
I'll
stop the
stop
video
the recording.
because
Recording.
sure. Yeah, please. Yeah, go ahead. Thank you.